Now, this one is very similar to one we did before, or ones we've done in the past, where if you plug in 0, you got problems actually in both of them. Both denominators make 0. But what we can do is we can actually combine everything that's in the parentheses to try to make this look a little different, and maybe we'll be able to cross something out. So if I do the math here, I have 1 over x plus 5 over x times x minus 5. The common denominator is actually x times x minus 5. So one of them already has it. So this is the only one that needs it. So now I'm going to have x minus 5 plus 5 all over x times x minus 5. So if you do negative 5 plus 5, that's 0. X over x times x minus 5. You'll see the x's cross out. So that means the limit as x approaches 0 of 1 over x minus 5. And now I can plug in 0, and that's going to be 1 over negative 5, which is negative 1/5. Okay, let's talk about one-sided limits again. And this one I'm going to end up using decimals for a little bit. So essentially, we've talked about this before, right? If you have that little negative sign, it looks like it's kind of in the power on the 3, but it's just a negative up there saying approach it from the left. And if it's a little positive up there, you approach it from the right. Okay, so if I were to just show you the graph real quick of the square root of x minus 3, you guys probably already know what it looks like. I'll go ahead and show you the graph. So we have square root of x minus 3. All right, square root of x minus 3. All right, so there it is. But if you try to approach it from the left of 3, right? So the idea is you're approaching it from the left of 3. You can't actually do that because it doesn't exist left of 3, right? We don't have any values that are less than 3 in the x that we can use. So this one you can't even do when you try to look at the one-sided limit from the left. So this one does not exist because we don't have any values for x that would be able to plug into this function. And when you look at it from the right-hand side, as we approach it from the right, you'll notice we're approaching 0. All right, so just something to think about when you're doing this. We haven't seen one like this yet. So just showing you it does matter if you actually have values in the function from that direction, if you will. Okay, let's look at this one. It's a piecewise. We've kind of done this a little bit with a table. Now we're going to do it using our limit laws. So if we're looking at approaching 2 from the left, then we're going to be using this first piece because we have values that are less than 2. So I'm going to plug in 2 into the first piece. So 4 times 2 minus 3, which is going to be 8 minus 3, or 5. And then for the part B, you're approaching 2 from the right. So that's values greater than or equal to 2. So I'm going to be plugging 2 into the second piece. 2 minus 3 is negative 1. Negative 1 squared is 1. And so when it asks for what is the limit as x approaches 2 of the function, right? We talked about this in a previous lesson. If they don't match from the left and from the right, then when you look at the limit as x approaches 2 of this function, you would write does not exist because they don't match. Okay. Almost there. We're getting close. Now, this one here is, you'll notice that if I plugged in 2, right, I would have 4 minus 4 in the denominator, which is 0. So one thing that's interesting here is if you factor the denominator, so I have x minus 3 over x times x minus 2. All right, you'll notice we can't cross anything out, but watch this. This is really interesting. The only piece that is a problem right now is the fact that if I were to plug in 2, I would get 0 when I plug the 2 into here. Okay? So you can actually split this up to be x minus 3 over x, right? Because that one's fine. All right? And then times, I should say, times the limit as x approaches 2 from the left of 1 over x minus 2, right? That's the one that's a problem. So if I do this one here, and I look from the left, I would plug in 2 to get 2 minus 3 over 2, which is going to be negative 1/2. All right, and then if I can use something we talked about in the last lesson, but I'll graph it for you to help you out. So we're doing 1 over x minus 2. So 1 over x minus 2. And again, we're approaching 2 from the left. Let me confirm. Yes, 2 from the left. So 2 from the left, you'll see we're going down forever towards negative infinity. So this limit, as x approaches 2 from the left, would be negative infinity. But we're going to multiply that together. I know it's weird if you never really multiply by infinity, but the key thing is if you multiply a negative times a negative, you end up getting a positive infinity. So that one is probably the most unique one that we've done so far. Okay? All right. Let's keep going. Now the squeeze theorem. I'm going to do my best to try to explain it, but as I said, I think you might find it to be a little bit easier to understand if you read the Calculus for Dummies. Essentially what this squeeze theorem is saying is that if you are unable to evaluate the limit of a function, or as x approaches a certain number, if you find two functions that have that are one of them is above the function you're looking at and the other one is below the function you're looking at, if those two functions, all right, that are above and below, right, think of them as like the bread of the sandwich. If those two have the same limit as x approaches that number, and they are equal to the one you're looking at, right, let's say the salami or the pepperoni of your sandwich, right, then essentially the squeeze theorem says that they must all have the same limit. So that's what this squeeze theorem is really talking about. I'm going to do an example, but I will say this is pretty tricky because it's going to essentially ask you to be creative and come up with the bread, if you will, of your sandwich for the squeeze theorem. So I'll show you how I came up with these two functions for the bread, but ultimately you're just going to have to get creative and try to guess and check if you're having trouble. Okay, so let's try this one. It says, applies the squeeze theorem to evaluate the limit as x approaches 0 of x times the cosine of x. So just right away, if I try to plug in 0, you're going to get 0 times, and the cosine of 0, right, if you know your quadrantals, the cosine of 0 is 1. So 0 times 1 is 0, okay? So essentially what I'm saying here is I know what it will probably be, all right, but I want to prove it using the squeeze theorem. Now, if I were to look at taking the cosine of any number, and I'll go ahead and graph the cosine of x. This might help your brain understand it. But if I were to graph the cosine of x, okay, and zoom in a little bit, you'll notice that my y values never stray higher than 1 or lower than negative 1, right? I'm keep going up and down between 1 and negative 1. So essentially what I'm looking at as x approaches 0, if I multiply this by x, right? If I multiply this by x, if I have the cosine of 0 is 1, right? The cosine of any number can be a max 1 or the min negative 1. When I multiply by an x, I can't go past the absolute value of whatever that x is, whether it's 4, 5, 6, 9, 10, whatever it is. So if I plug in an x, you'll notice that we have from the left to the right, you can see what we're approaching. And so what I chose for my bread functions, if you will, are the absolute valued functions. Right? So one is a positive and one is a negative. Okay? So if you look, I'll zoom in. If you look at my black and my purple V's, right, I chose those because they are, I'll zoom out. The green one is never going to be past the purple or the black. If I keep going, you'll see it never goes past the purple or the black. All right, so they are both above and below our function. All right, and then when you look at zero, they approach the same value for y as our green one. All right, so if I know the limit of the purple one and the black one as x approaches 0 is 0, then the limit of this green one must also be 0. That essentially is what we call the squeeze theorem. I know that is not really intuitive, right? But ultimately, that's something that we'll talk about more in class. Okay? All right, let's do the last one. Okay? So this is saying to evaluate this trigonometric limit, and they're giving a hint, right, from the textbook that the limit as theta approaches 0 of sine theta over theta equals 1. So if I try to plug in this 0 for theta, right, the cosine of 0, as we talked about on the previous problem, the cosine of 0 is 1. So that's 1 minus 1, which is 0, and then the denominator is also 0. So I can't just plug it in like I would hope so, but I can't. But if I were to multiply by the conjugate here, so multiply 1 minus cosine theta over theta times 1 plus cosine theta over 1 plus cosine theta, we would get 1 minus cosine squared theta. All right, again, as I mentioned before in the conjugate, you can multiply to get the middle pieces. They're just going to make 0. That's the whole point of multiplying by a conjugate. Leave the denominator separate for now. All right, so then you get 1 minus cosine squared theta. If you're using your trig formula sheet, you'll notice one of our Pythagorean identities is sine squared theta plus cosine squared theta equals 1. So if you were to move this cosine squared theta to the other side with subtraction, you would get sine squared theta is equal to 1 minus cosine squared theta. So that's actually what we have in the numerator. So I'm going to rewrite that as sine squared theta over theta times 1 plus cosine theta. Now this is kind of the how do I say this? This is the part where it's like, okay, I'm a little bit like I'm still with you, and then like, oh, now I lost you. Let's see if you can handle this. If you have sine squared theta in the numerator, you can actually split that up to be sine theta over theta, and then times sine theta over 1 plus cosine theta. I'm actually going to leave room for the limit here. So times the limit as theta approaches 0 of sine theta over 1 plus cosine theta. All right, and the hint is really where my brain knew to do this. If you look at the hint, it says the limit as theta approaches 0 of sine theta over theta is 1. All right, so I know this is going to become 1. And then if I plug in 0, and the one on the right, sine of 0, all right, is 0 over 1 plus cosine of 0. Cosine of 0 is 1. So 1 plus 1 is 2, and we know 1 times anything that's 0 is going to be 0. Okay, so that's what this one became. All right, I recognize this is a lot going on, lots of problems, lots of algebra, even some trig at the end, a new theorem called the squeeze theorem, which is not really that intuitive. So take a listen. Remember to read the textbook, read the Calculus for Dummies, try your best, and hopefully you'll feel confident.